So I'm not sure how to control the lights in this room. So hopefully you can read what's on the screen. If you cannot read what's on the screen, just let me know and we'll spend a bit more time trying to turn down these lights here in front. Lots of controls, but not for the lights anywhere I can find. So if anyone knows where the light controls are, that'd be cool. Oh, okay, great. So I believe I'm broadcasting properly on Zoom now with so on YouTube while sharing the screen this time. Just review. Oh yeah, we're going to talk about some statistical principles today. Not a lot of statistics. Again, this course will not be driven by statistics, but I want to give an introduction to kind of random or probabilistic thinking and importantly, give a sense of what happens when you do not have structure and data. You get some weird things that can happen that maybe is not what you expect when you don't have any really interesting structure. And so in order to say, I found something really interesting, you have to really be convinced that this wasn't just happening at random in the background because of just the natural random variation. So we're going to kind of get some insight into that today. Let's see. Before we get started, let me just remind a few things about the web page. Oh, what I want to do. Remind a few things about the web page. I posted yesterday's slides on the class overview. This was what is data mining, and then the ones on the syllabus here. In future, the ones about the class lecture notes, which will be kind of an overcomplete, more formally written than I'll go through in class, or document will be linked off the name of the topic. And then they'll be in brackets, kind of like a parentheses F. So typically it'll be what I'm writing on my iPad. That'll be what I'm scribing. That will be kind of linked off there also. There'll also be the video of the lecture. You can get there and get the YouTube video of the lecture and then some other notes. Okay, the other thing that's updated on the webpage has happened just before class, and I reserve the right to change it a little bit. I kind of wanted to get it up, but I have linked off of here. If you click on this link, you'll get the first homework assignment is posted. And again, I might change it a bit. It'll be mostly kind of working through implementing and simulating some of the stuff we'll be talking about today in class. So you can go through and look at the questions. These will make more sense after class. I just want to highlight a couple of things. I suggest you do stuff in LaTeX. And in fact, I have linked here a link to an overleaf document. And I believe I set it up so you can only view it. That means if you want to edit, you have to copy it over into your own overleaf. You can also download it. This will kind of give you the template to start. It lists everything in the assignment and tells you where to write your answers. This will, if you write it in here, it'll be easier for us to grade. You're welcome to do it otherwise, as long as kind of each answer and part of the answers is well documented, so we know what part to grade for what question. But I'm just trying to kind of do a little bit of prep work to eliminate all that part of the work that you have to do, so you can focus on the core part of the questions. So please check that out after class. It's not due until the day it's listed here in the table, which is September 8th, Tuesday, September 8th. So that'll be some more than a week from today, a week from next Tuesday's lecture. And it's due at, so at the end of the day. It will be turned into Gradescope. I haven't linked it up to Gradescope yet, but this will all come. And so again, the goal is to get it up at least a week before it's due, hopefully at the start of the week, ahead of when it's due, so you can start and take advantage of the teaching assistant hours twice before it's due if we get it up in time. All right, so that's the plan. All right. Okay, everyone's found the website. Everyone still knows how to use websites? Is that not too? Yeah. I think it's safe to start working on. I will post an announcement on Canvas when I say the official version is up, it's up in Gradescope, everything is all set. If there's any changes, they will be very, very minor, or there might be a typo in there, that sort of thing. We've kind of got it. I just wanted to get something up before class today, but I haven't done my final pass on. The TAs have looked at it, so I think it's okay. But if you see anything, that we've missed about it, please let me know. Yep.
Just so I really like that has changed a little bit. There are preferred Python version. Hopefully we should.
No, it's the code you would include. If you include code, put it in, paste it into the PDF document in a format we can read. We will, we will try and grade without looking at your code. Okay, so part of what we'll see today and what you'll see in this first assignment is actually the core output of running experiments, especially probabilistic experiments, is going to be some charts and some plots. And so we kind of know what those should look like and what the normal variation of those is. Myself and the TA are trained to understand this looks in the range of normal and this does not look in the range of normal. And so more and more when you're using AI, you will inspect whether it's correct through some sort of, you might want to write like a unit test and stuff. With probabilistic algorithms, with data analysis, is much harder. You have to tell it to plot it and look at it and think, is this correct? And so that's the core of what the assignment will be. We'll be outputting some plots of you running experiments. That's what we'll be grading. The code you can add in there so we can say, you got these for loops backwards or something like that. And so you almost got it. We'll try and give you some partial credit in the assignment, but not because we're going to deeply review your code at the grading stage. Yeah. This is turning into a really horrible way to evaluate homeworks in computer science. So, but what we'll be doing and what you'll be training to do is to look at the outputs and plots of stuff and understand, did this work correctly or did this not? All right. Great. Okay, good. So I'll keep reminding you of this until because I find it's useful for you all to have reminders. What can I say about that? Okay. Great. So what we want to talk about are statistical principles here. Great. So we're going to where did this go? All right, so the first kind of step is we're going to think of data. In this case, it's going to be a set X. Okay, we're going to use mathematical notation to describe stuff. It's a set, so it's X1, X2, up to Xn. And if for most of data analysis, the convention is to assume this data is IID from some sort of underlying distribution. So some distribution, these are the parameters. Okay, I'm writing this abstractly now. When this is useful, we'll study what the parameters can mean to depth, but there's some sort of parameterized distribution, and we're seeing these IID draws. What does IID means? It means independently and identically distributed. Okay, IID. So it means that we're making a bunch of observations from some distribution of the world that we want to understand. Okay, each view of the world is independent. So if I make one draw, it does not affect what the other observations are. They're going to be identical draws. They're all coming from the same distribution we want to understand. So it's distributed means that there's some, should think of this probabilistically. All right, so this is not a perfect model of the world at all, but this is kind of often underlies a lot of what justifies why we use the mathematics, why we use the algorithms that we do. Okay, and the world is varying over time. If you make an observation and you act on that observation, it will change what the future distribution is. Every observation, it may be that you don't draw you can't draw the same thing twice. You do something without replacement from a finite distribution. These can all happen, okay? And so it's not a perfect view of the world, but it is a very convenient view of the world, and most of modern statistics and machine learning is built on top of this particular view of the world. Okay, so we're mostly going to be looking at this. And so one of the views of statistics, one of the key things that people look at is what happens as n. Remember, this is the number of the data points. What happens as n goes to infinity? Okay, we don't ever get to infinity, and especially in kind of a computer science, data science world, our data is always actually finite. Okay, but as it gets bigger and bigger, you get a better and better estimation. Okay, and I'm not going to go through this in detail today. I hope you've seen this before class, but the central limit theorem okay. I do not have the best handwriting, and it will get, I don't know what iPad's doing. Oh boy. Okay, that made it worse. Theorem. Okay, the central limit theorem tells us in various ways what can happen as n goes to infinity. We get a better and better estimation. Things look kind of like the expected value of the distribution if you set stuff up the right way. There's lots of ways to formulate it. We're not going to go through that today. Okay, but a lot of statistics is based on this, and we as data scientists want to figure out how to reverse engineer to say, how big does n need to be for me to get a certain amount of accuracy? How many samples do I need to draw? Or if I have a fixed data set that I downloaded someplace, how much can I trust the analysis I'm doing? Okay. All right, so we want to study, we're going to kind of think about data in this way. We're making observations. I haven't said what the data looks like yet, okay? And this will vary a lot throughout the semester. We'll think of different ways the data can look like, but we often have a set of observations. The fact that they're a set, right? So the fact that I have the curly brackets there means that the order of them does not matter. I just have a set of n observations. And that I'm going to look at these in some way to try and understand the structure. What is each lowercase xi, right? That structure will change depending on the sort of data we look at throughout the class. Okay, what I want to do today is to look at a particular form of data where we're going to say that each xi is going to be in some universe, let's say, of size m. Okay, this is an abstract representation of this is kind of a shorthand notation. When I put the square brackets around a number, it means I'm looking at things 0, 1, 2, up to m minus 1. Okay, so I'm looking at a discrete universe of size M, and I'll think of those from 0 to m-1. From most of computer science, if you're not using MATLAB, then you start counting at 0. So we start counting at 0 here. Okay, but these are representations. You think of your storing data inside of an array. Each array corresponds with some actual object, some very interesting things to think about here. These could be IP addresses. Okay, if your IP addresses, then M equals something like 10 to the 16. That's a pretty big number, right? If you're thinking about words in English, okay, then this is probably, M is probably, well, I would say your working vocabulary is probably much smaller, but you can build a pretty good language model and communicate on most stuff using no more than 100,000 words. And most things don't capture, let's say if you go to 300,000 words, you get to almost everything that's been written, including things like emojis and stuff. What's typically done with these language models is you break stuff down when it gets really rare into these things called tokens. There are again about 100,000 tokens which are used. Okay, so think of words or tokens. So think of tokens in a language model. You might have like 100,000 of these. And then if you think of people, then if this is in the world, then this is was it like 6 billion people, or maybe this is 360 million people if it's just like in the this is in the world, or if this is just in the US. Okay, so these are some fairly big numbers. And so we want to kind of think on this scale. And so in particular, now I want to put, so this is our domain. We're going to just study just for this lecture. We'll come back to versions of this, this problem a few times. And then I want to put a distribution on top of this. So I want to say each xi is iid from some distribution, right? This is my distribution. And I'm going to say this is equal to the uniform distribution. Okay, so that means each I in M has the probability that xi equals, so that should be j, for each j in M is equal to this value j, right? So one particular IP address, I create a random IP address. The probability its IP address j is, this is the probability, it's 1 divided by M. And for j that is not in M, then this probability that xi is equal to j is going to be 0. Okay, so I have M different possible options. Each of them is going to be equally likely. Okay, so this, that I want to study this for for two reasons. One, I think it's this distribution is pretty natural. Okay, and so for instance, if I am building a hash table, which is a super important sort of data structure, hopefully you've learned about, this is kind of the distribution I need to generate like inside of a hash table. I'll say a little bit about this on the next slide. And it also kind of represents kind of no structure. Okay, so I mean, you could argue that having a perfectly uniform distribution is a really interesting structure, but it's not going to have like a weird sort of anomaly or a set of IP addresses, which is way more popular than other ones, or some weird correlation I'm trying to find. It's basically nothing. Okay, there's not really much going on here, but we'll see that it will, if I study a set of data from this distribution, some of the kind of properties I'll find about it might be a little bit unusual, and so not what you expect. Okay. All right, before we get into this, I just want to say a little bit about hash tables. Okay, so a hash table is a really clever way to store a set, and I just want to be able to return is something inside of a set. So one of the things I store an array, call this A, and this array is basically my set M, right? So I think of a long array, and I can index into it 1, 2, up to the M thing. And so if I just want to store if something is in the set within each entry inside of this array, I store 0 in most items and 1. This one is the interesting point. That means there's something in spot 2. I've stored a bit if something is there. I can store more information. I can store a pointer to where the actual information is to. All right. The other ingredient I need for the hash table is I'm going to need a hash function. Okay. And this hash function is going to go from some sort of domain. This is often kind of like a string of input that's describing my input, and it's going to map to my domain M. Okay, so I'm going to take my input, whatever that is, I will convert that into some sort of string representation. It can be a number, but I write out the numbers. It could be a word, it could be text, it could be a file I turn into a string, and I'm going to map it to some M, and I want it basically to map randomly to one of those cells, so that if I have 2 different items, it's unlikely they map to the same thing, right? So I want the property, I roughly want the property, this is called a uniform hash, if the probability that J equals probability of J prime equals 1 over M, if J and J prime are both in the set and J is not equal to J prime. Okay? But this hash function, this is deterministic. Okay, deterministic. That means there's no randomness in here. So I've talked about probabilities. This is the probability that these are equal is equal to 1 over M. So that's the probability they're equal, but this is a deterministic function I've defined so far. So this shouldn't quite mess. The reason I want this, if I take the same item and I hash it twice, I always wanted to go to the same spots. So I need it to be deterministic. So when I see the same item again, I know where to look for it. Okay, but these hash functions, but I want some probabilistic statement about this. So how I typically do this is I have a seed. Okay, we'll call the seed S. And this is basically a randomly chosen string. Or actually, this is probably better to call this a salt. Okay, often it's called a salt. It's a randomly chosen string. And so actually, when I apply this, I actually apply hash of J concatenate with S, okay? Or hash of J prime concatenate with S. Okay, and so this salt S is like, let's say it's a random number 42, right? If you use an AI, it'll almost always generate 42 for the random salt for whatever reason. Probably because of probably because of Hitchhiker's Guide, but it will like to generate 42, but you should mix this up sometimes. And so now if I hash J concatenate S or J prime concatenate S, well, now it's a different string. And because S was chosen at random, then the probability that they should collide, this hash function should hash things that are different, likely to different spots. It's deterministic, but it's something that's kind of invertible. It's not invertible. So if I know the hash value, I typically I typically cannot invert it to go backwards. And there are some studies that are fast, that are implemented. This is often built into your code. You don't really need to know the details of how to use this. A common one is, so it's called like the SHA-1 hash. Still works reasonably well. There are other faster ones which will be used as default, but these are often designed for cryptographic purposes because we don't know how to go backwards once we've hashed something. If you have a secret key for a crypto reason, you don't want someone to be able to figure out what your data is from the secret key. And so this is an example, and there's a little bit of detail in the notes about how to implement this if you want to do that. Okay, but this is a random process. Once I've picked a random seed, then if I put in some data, and the data is, I'm getting a bunch of these J1, J2, J3, J4, and I'm putting them in this hash table. They look like they're uniform randomly from these M so possible values in the array. Okay, so this seems like this is the core of how hash tables work. It's a fairly natural sort of distribution. Okay. Okay, good. So I want to talk about another fairly natural place this occurs. This is often referred to as the birthday paradox. Okay, and this will be a more tangible version of this. And we're going to look at M equals 365. We're going to think of these are the days of the year that people may have their birthdays, right? So these are the days of the year, okay? And so we're going to simulate this. And so the birthday paradox is that I can say with very high confidence, there are going to be two people in this room who have the same birthday. There are about 100 people in here, more registered, might be 120. I'd say before we get to the first 50 people, we're going to find people who have the same birthday. We could probably run this twice if we wanted to, and independently on the two sets, be very confident. Probably a good chance with 3 times each. All right, so we're going to run this here, and what I want you all to do, you do not have to share your birthday if you don't want to, but then think of another day of the year, and you're going to report this when I ask you. Okay, January, February, March, April, May, June, July, August, September, October, November, December. Okay, so we're going to go through and I'm going to call you. I'm going to write down the day of your birthday on here until we see a match. Start over here. Yeah. May 14th. November 25th.
July 1st.
July 1st. March 30th. February 2nd. April 12th. January 25th. August 18th. January 12th, November 13th, January 17th, February 17th. Did I skip you? Yeah. April 6th, August 16th, September 22nd, August 10th, September 13th, May 23rd, May 13th, okay. December 26th, May 29, March 23rd, okay, there. August 19th. So September, December 24, okay. December 14th, July 18th. Where are we? It's Argentina. June 2nd, okay. February 28th. March 31st. June 16th. Okay, June 16th. November 20th. February 16th. May 10th. Okay. June 28th. January 27. All right. October 8th. Oh, we didn't have October yet. All right. May 31st. July 28th. May 9th. 10th. May 10th. Ah. Okay. Okay. That's a collision. All right. Very good. Very good. Just when you're starting to get tired of this exercise. All right. Great. Okay. Okay. So how many birthdays did we go through before we got to this? Someone count these. 38. All right. Okay. So we'll see that this is around where we would expect with this. Okay. So this was only, if we only had the first half of the 38 people in the room, maybe half or a quarter of the room, we already had a collision. Okay, it didn't matter what the date was. That's important. I didn't choose what the date was going to be ahead of time, but we found some collision in here. Okay, only going through 38 birthdays. We didn't have to go up to 100. We didn't have to go up to 365. All right, all right. So why does this work? So how many people have seen stuff on the birthday paradox before? Is this kind of new? Is this kind of like, whoa? Okay. All right. Well, let's go through this quickly. The kind of details of the calculations are not the most important thing, but I want to kind of give you a sense of this. So I want to write down the probability. And so this corresponds with the birthday paradox. This is kind of how long did it take until I have it's December's off the bottom. Okay. Until I have a collision in my hash table, right? So if I have a collision in the hash table, then I have to do extra work to store stuff, or it breaks. I could have a mistake here. So this window I get a collision in the hash table is kind of an important thing to understand, right? So I want to know the probability of a collision with n samples, okay? And I'm going to fix m equals 365 And so the probability with n equals to 1 is equal to what? If I take one person's birthday, what's the probability there's a collision? 0. Okay, if I have probability for n equals 2, this is going to be what? Yeah, it's going to be 1 over 365, 1 over m. The first person goes anywhere. The second person, it's 1 out of 365 that they collide with the first person. Okay. We can then ask probability of n equals 3. Okay, what's the probability with n equals 3 that I have a collision? Yep. 2, okay, yeah. So we can think of the first guess is 1 over 365. And you said to the power 2, gonna say there are different ways we can have collisions. The first two people can have a collision birthday. That could have already happened. Then the third person could be a collision with either of the first two people. Right, so I get 3 different possible collisions here. Okay, and so I'm going to write down as an answer. Nope, that's not. Okay, it's 1 over 365 to the power 3, because there are 3 possible collisions. In general, if I have n, if I extend this logic to in general n, it's going to be 1 out of 365 to n choose 2, right? This is equal to n. Let me actually write this up top here. This is n choose 2, and this is going to be n times n minus 1 over 2. This is roughly, we can think about this as n squared over 2. Okay, I can look at all pairs of people. They're roughly, if they're n people, they're roughly n squared pairs. But I don't want to count the pairs twice. It doesn't matter if it's person A to person B or person B to person A. Yes. Yep. Yeah, this is not quite right. You are exactly right. This is not exactly the right analysis here. This should actually be, let's see, 1 out of 365 was the first two collided, and then I can this, I think 1 over 364, because then yeah. We'll go through this a little bit. I'm not going to go through the exact analysis because it's actually so quite nuanced, but this is a good point. This is not quite the right analysis here, because if the first two people did not collide, then I know there are 2 possible different situations. But if the first two people did collide, then I don't need to worry about the third person. So you can't do choose. You have to write out some expression. But I do have the formula written in the notes. I'm not going to explain today. I want to kind of hit the high level points here. Okay, but you're right. This is not quite the right expression. Sometimes it's okay to do this in day analysis. You want to get the big picture, and then you want to think, okay, did this give me approximately the right thing? We're going to kind of go through this exercise, and we'll come back to it, and this will be a fun thing to work on your own afterwards. All right, but I want to look at this expression because it's for the part of the analysis we're going to explore, it's close enough to being correct. Okay, so this is roughly equal to, approximately equal to 1 over 365 to the power n squared over 2. Okay, so I want to say how many, I want to know when this reaches more likely than not. Okay, I want to solve for when does this equal to 0.5. How large does n need to be until this equals to about 0.5? That means more likely than not, I'm going to have a collision. Okay, so I'm going to replace 1 over 365. This is 0.997 about. Again, this is another approximation. And then I'm going to do n squared over 2. Okay, and let's plug in an estimate here. Let's say, what if n is equal to, what was the number we had? 38. Okay, then I'm going to have 0.997 to 38 squared over 2. This is the probability I'm going to have a collision. Let me type this in, 0.997 to the power 38 squared over 2. This is something didn't go right. I asked this in Google and it did not give me an answer that made sense. Let me. Okay. So this probability is going to be approximately 0.1142. So this is the probability that so this is the probability I do not, so it's not 0.997, this is probably I do not have a collision. Okay. And so I want 1 minus that I'm going to have so I'm going to say, okay, so I made a mistake here. This should be 1 minus 3, 1 over 365. And this should be one minus 1. So the probability I do not have a collision, and then I keep going, and then 1 minus the probability I do not have a collision is the probability I have a collision. Okay, and that is going to be this is 1 minus 1 over 365. So now I have 1 minus 0.997 to this power okay, and so that's 1 minus this number, and this is going to be 0.882. Okay, so with 88 probably the time with this rough analysis, 88% of the time, if I go through 38 random people, that some pair of them will have the same birthday. At least one pair of them will have the same birthday. Okay. So where does this number break even? It breaks even, or I get to about 0.5. This happens at about n equals 23 people. When you get to about 23 people, about half the time, you will have found a pair of people who have the same birthday. Okay, if I plug in 23 squared over 2 in here, I'm going to get roughly 0.5. as I'm doing this. Okay, and so the main takeaway I want you to get from this is that where does the expected, like, when should we expect as a function of n and m? So we have that the probability of a collision for n equals about 0.5. When n is equal to roughly, it's going to be square root of m. Okay, so as m gets bigger, my hash table gets bigger, right? Let's say the hash table is going to be so 20,000. I have 20,000 entries in the hash table, right? Then around when do I get about probability 0.5 of having a collision? I have 20, if m is equal to 20,000, or yeah, so let's say 20,000. So if m equals 20,000, then I have 2m equals 40,000, and square root of 2m is going to be roughly 200, right? So if I make my array very big, 20,000 is reasonably big, and I put only 200 things in, I kind of expect half the time I'm going to have a collision. So when you build hash tables, you have to work a lot on the strategy of what happens when you have collisions, even though it's equally likely, each cell is equally likely, the collisions happen, right? And they happen fairly early on in the process. Okay, so yeah, seeing a bunch of objects and think they're actually uniform in some space, you should not be surprised if fairly early on in gathering data, you kind of have two things very close to each other, and that very close to each other might be mapped to the exact same kind of representation space. Yes? Yeah. That's right. Yeah. Right. So there's, yeah, so like words in English language kind of follow like a Zipfian distribution. This is cool. So if we're using a hash table, if we see the same word twice and we're just storing, did we see that word? This is totally fine. So that hash table, it's keeping a set. It doesn't keep track of the counts of things. We'll see a data structure layer in the semester where you actually adapt this hash table to keep counts of things. And then we'll see how to deal with this chances of collisions to still maintain counts. So it's something we'll deal with this sort of situation later on. And then it turns out if you have like a Zipfian distribution of data, the size you need for the data structure to be accurate actually improves. You can do better because you have a lot of the same thing. Well, I know then that counter is very accurate. Okay, this is something we'll talk about right before fall break. Okay, cool. This is interesting. There's a lot to unpack here, but that's one direction we'll see. Okay, these are good questions. Well, there'll be other ways you deal with language, and that are, this is kind of the elements of how we dealt with language when for the very first search engines were built, like Alta Vista. Probably have never heard of Alta Vista, but it was built on using hashing in a very cool way. Now we use other techniques that we'll mostly focus on over the semester. All right, but this gets me into what was, okay, and I wanted to ask this not just because you were kind of very astute here, but what was wrong with this analysis? Okay, there was some stuff that kind of broke in our analysis here, and I wanted to get to that. Let me write this more cleanly. The probability of a collision at n was roughly 1 minus 1 minus 1 over m to the power n. Let's just simplify it to say n squared over 2. Okay, so this was roughly the analysis. I said the probability of finding a collision was roughly 1 minus 1 over m, right? To the power n choose 2, or n squared over 2. And there are a lot that went into this. We went from birthdays are a uniform distribution to some math where I didn't quite handle the dependence. What can we say was wrong with this analysis? So birthdays are not uniform. Oh, how so? How so do you think birthdays are not uniform? Yeah, okay. This is pretty hard to see. There's slightly more people born in the spring, it turns out, but it's pretty small. It's for the humans, it's pretty uniform. For some animal species, there's certain times a year they almost always have the babies, but for a human population, it's very close, very close to uniform. It's not exactly uniform, but for the purpose of this analysis, this is not one of the major kind of ways that it's not quite right. Yeah, but if you were to look at something like people who made it into the NHL, the birthdays are very not uniform because there's a often selection function for people who are a bit bigger to do better in the sports. And so people whose birthdays were right before so they're older based on where the cutoff was in Canada, it turns out, that those people tend to be more likely to make it the NHL. So some places you can see this, but uniform across the population is pretty close to uniform. This was, if I'm a little bit more careful, I can write down the exact probability here. It's not too far off from this for some of the stuff we did, but it's not really a worst case analysis here. This is not, I'm pretty close to writing down the exact thing. It's not quite right, and you can look in the notes to see how to fix it, but it's not a worst case analysis. Yeah.
Wouldn't it then be the case that more modal distribution would be, you would have a higher chance of a collision early?
Yeah, okay. So if instead of uniform, I did have like, it looked like a discrete normal distribution centered someplace, and so the tails were very low, then you have a much higher chance of collision. This would be true. If it was non-uniform, then you would have, yes, you would have.
That's what I meant by
great. Like okay. Yes, good. Okay, yeah. All right, there's another hand up there. Or someone else have a suggestion? Yes? Okay, great. So no, so leap year. So there's actually M equals kind of something like 366 maybe, because there might be someone with a February 29th birthday. This occurs roughly once every 4 years, but actually not exactly 1 every 4 years, because every something like, was it like 100 or 1,000 years, they sometimes don't have a leap year. And so it's kind of a mess to deal with this. Okay, yeah, so again, we made a mistake. We threw away some very low probability events. This is not an unnormal thing to do in analysis. But yes, we didn't exactly have the right domain here, and figuring out how to map it to the right domain is actually surprisingly kind of is is messier than it sounds like. Good point. Yes. Yep. Yep. Great. So the probably is wrong. What values of m and n does it go wrong? Right? Can you point out an example here where you realize, okay, things have gone totally off base? So for the range, when we're in the range of something like n equals 23 or 38, this is pretty close to. It's going to give us about the right probability up to a few digits of precision. Okay, and I admit that I think for this purpose of this lecture, it's not worth. Didn't want to go into details, but what happens? So there's yes, the analysis should use factorials, but what range of this analysis does this bring? For n equals 0, 1, 2, 3, even it's pretty close. High values of what? Of n or m? Yeah, okay, great. So what happens when n gets large? Okay, so usually this won't happen in simulations. We don't have to worry about it. But what happens when n is larger than m? Let's say I had 400 people in this class. There are only 365, 366 birthdays. If I plug it into this formula, the important thing is this formula is always going to be, this is always going to be strictly less than 1. Okay, so I'm taking a value which is between 0 and 1. That's the 1 minus 1 over m. That was our 0.997 approximately. And then I'm raising it to some power. When I raise it to some power, a very big number, it's going to go down, but not down all the way to 0. So this is always going to be less than 1. But if I have more people in here than there are birthdays, by the pigeonhole principle, I have to have a collision. Okay, so this analysis is kind of good for some range of parameters. Okay, and so sometimes I'll lie a little bit in class to give you a simplified view, and some of you who are bothered about the factorials, which is a very natural thing to be bothered about, then I will make sure to point to where the actual analysis is if I can't go through it. But sometimes we'll simplify analysis for some range of parameters, but you need to pay attention to this. It may not work the very extreme ranges beyond what you modeled. Twins, great, yeah. So if I had twins, so I've had twins in this class before, and they had the same birthday. It's kind of cheating as well, right? If I looked at if they were only one of them in the class, it wouldn't violate anything. But because they were both in the class and they were at the same age and same interest or something, they ended up both being in here. And then that increased the probability of having a collision because they had the same birthday. Right? So some other stuff like this can happen that can violate. This is more like, this is a bigger issue than the non-uniformity of the birthdays. And maybe, I don't know, it depends, maybe on par with whether it's 365 or 366. Right? The twin rate is higher than that, but the fact that they're both in the classroom drives it down, so it's not too high. Yeah, that's another interesting point. All these sort of things can happen in your analysis. Again, what I'm going to try and guide you into this class is kind of how to model things that are mathematically useful, and we'll have to make certain approximations along the way so that we don't get boiled down too deep in math that is not really helping our understanding, or is modeling stuff that is very rare and is not going to be really driving what we're seeing. And some other phenomena, like do we have twins, or is birthdays non-uniform, or 365 or 366? Those might be on the order for ranges of M in 23 to 38, more important of a deviation than the change in the analysis, whether I properly dealt with the kind of the factorial expansion or I did this approximation. For larger ranges of n, this would change. Then it becomes raw, right? So we'll kind of guide you to this, and this sort of approximations you'll use in the analysis. Yeah. Yeah, so I'm saying there are when I mean this is the first way of thinking about this is that you have n choose for n people, you have n choose two pairs of people, and each one, if I look at them independently, they have a 1 over 365 probability of colliding. Okay, but they're not independent because of, yeah. Okay, great. And if you look in the notes I linked, I describe a bit more of what the actual analysis is. Okay. Okay, I want to go and talk about another variation of this. That's kind of a twist on this problem called the coupon collector problem. Okay, and so this is when I was young, this was introduced as you want to go to McDonald's and you want to get a Happy Meal, and every Happy Meal comes with a toy, and you want to collect all the toys. Okay, every time you get a Happy Meal, it's a random toy, supposedly. It's probably not entirely true again, okay? But I want to collect all the toys, or I have like a box of cereal. I think this was when my dad told me about this. He said he would get cereal that have a toy inside the cereal. Does that still happen? I don't know, but you'd want to get all the toys, and then you'd have to keep buying more and more boxes of cereal. And so now we're saying that I have M, so coupons, okay? So now maybe it's like Pokemon, right? That's a modern analogy, right? Maybe. Okay, I have N Pokemon, and I have M Pokemon, and I want to collect them all. Okay, every time I open a Pokemon pack, let's say I'm gonna have a random, so Pokemon, right? You probably 10 random Pokemon, but let's say 1 random Pokemon. Okay, I'm gonna collect all M Pokemon. How many packs do I need to open? Okay. Many packs N to open to get all M. Okay, so I want to figure out how many packs of these do I have to open? Okay, and so this is called the coupon collector. So for the birthday paradox, we're finding the first collision. This was square root M, roughly. The rough order of magnitude, square root M. What do we think? How many, roughly, ignoring constant factors and smaller order terms, what do we think the number of N should be as a function of M? Okay, so what do people think? Roughly, how many packs do I get? I get 1 Pokemon card in each pack. I'm assuming it's uniform. Roughly, how many packs do I need to open to get all the Pokemon? Yep. Okay, roughly 2M. Okay, that's a good guess. Other guesses? Think that's right? Yep. All of them. All right, all of them. M is finite, so so it needs to be. So was all of them as a function of M? or it's independent of M. Yeah, well, let's say we're assuming now there's one, I don't know, are there rounds of Pokemon? What is it called? And you're opening packs from the same round. They have the same distribution. There's one really good card in every pack. That it's uniform. You want to collect all the really good cards. Okay. M packs. So we say exactly M. So if I get M, I could get all of them. Okay. Thinks it's more than M? Who thinks more than 2M? Okay, what do you think it would be if it was more than 2M? 2 to the power M. Okay. 2 to the power M. Who thinks 2 to the power M is right? Okay. Yeah. Oh, you're agreeing with 2 to the power M. Okay. Okay, 2 to the power M, it's pretty big. It's not going to be that big. Okay, that would be kind of, I know it's hard to get all the Pokemon, but that's because they don't make them all equally like. Okay. All right, so we're going to go through this analysis very quickly again. I think I'll be a little bit, that you can get a pretty close analysis here. And let me just do this on the next slide. We're going to say that, so we're going to say that I'm, so Ri is going to be the expected, or let's say, actually, let's not put expectation into it. Let's say the number of trials to get so I Pokemon. Okay, so I distinct distinct Pokemon. And I want to look at the transition Ti, which is going to be Ri minus Ri minus 1. Okay, so this is going to be the num trials to go from I minus 1 to I, right? So I found I minus 1, and then I'm going to start counting how many more packs do I need to open until I get one that's new. Okay. Okay, so we know, for instance, that R1 equals T1 is equal to 1. So the first new thing I get on the first trial. Okay, and so the total number of trials I need, so Rm is going to be equal to T, uppercase T, which is going to be the sum of I equals 1 up to M of Ti. Okay, so it'll be easier to analyze Ti because Ti, I am going to have just one event happening, and I want to look at the expected value of Ti. Okay, so that means that I'm going to have M trials, right? I'm going to do a number of these trials of opening these packs. And so this is going to be 1 over the probability of seeing a new Pokemon, right? The probability of seeing a new Pokemon is going to, so it's going to be 1 over the probability of something new, which is going to be 1 over, okay, the probability of seeing something new. This is going to be the number of new things which are left, which is M minus I divided by M. Okay, of the M minus I things that I haven't seen yet, if I hit any of those, I get something new. All right, so this is equal to M over m minus I. And so that means this sum of I equals 1 to m is going to be m over m minus I. Okay, and this is, I can pull out the m, and I'm going to say that I'm going to count from, let's say j equals 1 to m of 1 over j, where j equals m minus 1, and m minus I. Okay, so I'm going to do a change of variables. The j, and this expression is easier to look at. Okay, so this, it's the same thing. I'm counting from 1 to m, but but this m minus 1 is easier to think of, or m minus I is easier to think of j, because it's going to see all the different things, right? So I've done a change of variables, but I get this expression. M, that I just factor out front, times the sum from j1 to m of 1 over j. This is known as this expression is known as hm. Okay, this is the harmonic number. Okay, and we know that this is going to be very precisely known. This is equal to n times some constant plus the natural log, or sorry, this is going to be equal to some constant times the natural log of m plus some smaller order terms. Okay, there's some very small terms that are meaningful for very small m, but as m gets big, these become not very relevant. And this constant is roughly 0.577. Okay. So if I plug this into here, this means that t is going to be equal to m times 0.577 plus natural log of m, roughly. Okay, so the answer was roughly m log m. So not too bad, not 2 to the m, but distinctly bigger than something linear. Okay, and so one way of seeing this is you can think of, if I look at ti for I in, let's say, 0 to m over 2, then the expected value of ti for the first half of them I get is roughly is in the range of between 1 and 2, right? So let's say this is roughly 2. The expected number of packs I open is going to be at most 2. Okay. If I look for ti for the expected value of ti for I in, let's say, m over 2 up to m over 4, well, then this will be at most 4, right? And when I'm in m over 4, sorry, it should be 3m over 4. 3m over 4 to 7m over 8. This is going to be at most 8 things I have to open. Okay, so I'm going to get roughly, I can think of these values T1, T2, up to Tm over 2. And all of these are roughly 2. These take me roughly 4. These take me roughly 8. These take me roughly 16. And eventually this last one here, I expect to take m trials to get this last one. This last one becomes more and more painful. They're exponentially increasing, in the number of trials I have to do. So there is some exponential stuff happening here, but that it really doesn't get to the exponential until the very last one. So the last one takes me roughly n times packs to open. The second to last one takes me roughly n divided by 2, or m divided by 2 here, right? So it kind of decreases very quickly from the end here. So the first one I go through very quickly. I basically is linear, and up to here, this 2m intuition was approximately right, but it gets really hard at the end here. And if some of the Pokemon are much harder to get than the others, and those are the ones I still haven't gotten, then it gets even harder at the end. And so you have to keep, keep getting all of them, right? So you'll never get all of the Pokemon, unfortunately. Or maybe that is fortunate, right? I used to collect baseball cards as a kid, and you could get all the baseball cards. I had a friend who got all the baseball cards. He got so many baseball cards, so many duplicates. Okay, great. So what are the big, so this is kind of another analysis where you can roughly approximate this. In order, you want to see everything in a set, they're all uniform. You think, okay, I need roughly linear number of things to see how many I get, but I'm going to get this extra. I have this extra factor here of this log m factor that also shows up. So it's not just linear, but there's an extra log m factor that shows up in order to see everything at least once. And there's analogs to this with so some sort of continuous data where I don't have a discrete set, but I want to see something in every possible region of the space. Then you also get this extra log m factor here, where you have to kind of oversample to see every region of the space. And this is kind of annoying. You don't get perfect coverage, even if it's uniform. If you see holes in your data, it's not necessarily because that the data, there was something missing in that area. It just means that there's natural variation where you don't see everything until you've fairly largely oversampled it. Okay, and so when you're looking at your real data and you see either a collision or things really close to each other sooner than you would expect, well, kind of you should calibrate this with this this birthday paradox analysis, where you expect roughly n equals square root of m before you start seeing collisions. That's pretty early in the process, right? If I have what our example, 20,000 things, after about 200, I'll expect to start seeing these collisions, okay? But if I want to see everything, I have to oversample by a factor of log m. Log m for 20,000, this natural log, so what is that going to be, like 20, 15 or 20? But so that means a factor of 15 or 20. So that means if I have 20,000 things I want to see all of, may have to sample at least 10 times that, so maybe 300,000 things to see one of each of 20,000. That's a lot more to see everything in every region. So we can't just look at data and say, there's a collision, these are too close, or there's an open space. We'll have to kind of be a little bit more kind of see a lot more examples of stuff to really trust the structure. Okay, so we'll kind of see more of this throughout the semester. Your homework will be simulating both of these experiments and kind of seeing what happens for different values of n and m. And we'll be matching it with the analysis. You'll have to look at either these rough analysis and see how close did you actually get. Because when you're doing a randomized algorithm, it might go wrong. One time I ran this experiment, I got to like 50, 60 students before we found a collision. Was that totally unexpected? Or was that kind of in the range of what you would expect? Okay, so you need to kind of match your randomized algorithms with analysis to understand. Okay, we'll end here and get back to this next lecture on Tuesday.
Just a question about the midterm. Is it going to be like